Alright, welcome back to Soils and the Environment. We're going to be looking at soil and water today, and you can see a summary of some of the things that we're going to be doing in this talk. We're going to sort of stand back first and look at the hydrologic cycle. Then we're going to look at the water molecule, then adhesion, the forces of adhesion and cohesion in that matrix, in the soil matrix of the water molecule, and the molecule between water molecules, and then the molecules and sand or soil particles. We'll look at surface tension and capillarity, soil water energy, soil water capacity, and then a few measurements as well, and then what that implies for soil water management, because of course if we don't have moisture in soil, plants won't grow. A real simple truth that we have. So let's carry on, and let's start and look at the water cycle. I just wanted to kind of give you an idea. I don't want you to sort of memorize the numbers or anything, but what I wanted to sort of show to you was that there were a number of processes that we had. We have precipitation, which is rainfall, evaporation, and transpiration, which is obviously water going back up. Evaporation being purely off the surface of soils and water, whereas transpiration is plants actually using water to cool themselves for their own metabolic processes, pulling it up off the ground and then sending it into the atmosphere. We have runoff. Now what you don't see here is infiltration into the water, and obviously we have pools of water, if you like. So these are fluxes, and then these boxes would be pools of water. And so one of the fluxes would be infiltration, which then ends up either in near surface water or in underground water over here. So I thought I'd just give you, or reservoirs, these things are not pools, they're reservoirs. I just wanted to give you at least an idea of the general processes. In soils, we're very interested in the process of infiltration, because what doesn't infiltrate runs off. Okay, so let's go on to everything over here is dependent on solar energy. The sun is going to drive everything, and you'll see that. On a watershed basis, we see this again. This is maybe a little bit more explicit. Rain and snowmelt really contribute to the moisture in the soil. Some of it infiltrates, some of it evapotranspirates. And what doesn't infiltrate or evapotranspirate is runoff. And in natural systems, we find that this component is very small. In built-up systems or disturbed systems, we find that this component increases. We have an unsaturated zone in the soil system where you have a mixture of air and water in those pore spaces, and then you have percolation into your saturated water, which is essentially your water table, and you can see your groundwater then is what contributes to stream flow the most, or at least not the most. That's what it should be. A good clear stream is mainly fed by groundwater. If it's nasty and dirty, most of that water is coming from runoff. We have percolation and then seepage into your deep saturated zone or aquifer. But I wanted to show you these processes again. These are the things we're most interested in as soil scientists. This formula over here is the change in storage, or the change in water in that system. That's infiltration, less evapotranspiration, less your deep seepage, less your groundwater that discharges to your stream channel. So delta S is the change in how much water total is in your watershed system. There are a couple of other things. Runoff is precipitation, and that's also snowmelt, minus infiltration, minus evapotranspiration. So you can't really control evaporation that much, and you can't control precipitation. So if you can control infiltration, you can reduce that number. And then finally, your stream discharge is runoff and groundwater. You want to maximize the amount of groundwater flow to your stream discharge. And when you do that, you increase your water quality significantly. South Carolina water budget, I won't dwell on that too much. We look at this in aquatic sciences. But it's interesting, my friend Bud Barter, who used to be the chief hydrologist at the DNR, said, you know, we have about 4 times more water than we need in South Carolina. Yet it's not, what happens is it's the timing and placement of that water that's a problem. Most of that water might fall in the winter and spring when evapotranspiration rates are not very high. In the summer, we also have a lot of precipitation, but you then have very, very high evapotranspiration rates, and you have longer periods between rainfall events, and you find that the water, that at least soil moisture, goes down, and soils dry up, and you lose crops, and you know it affects your ecosystem as well. Okay, so here's kind of a situation in South Carolina. This is your precipitation, lots of rain in the May-June period, but at one stage or another, your evapotranspiration is going to exceed your soil, exceed your precipitation. And this is where your plants are going to use soil moisture. This is also the period where your plants are growing the most. In the cooler seasons, we have a lot more aquifer recharge and runoff. So let's go and have a look at soil water. I am borrowing these slides from my friend Pam Thomas, who is a soil scientist. She got a PhD from the Hokies, and she's way better than I am at making these slides. But here we go. We've seen this many times. It's the ideal soil with the solid and the void space phases, if you like. So the solid phase and the pore space, the solid being mineral and organic matter, and the pore space being air and water. So what we're going to look at is these concepts in, I've already mentioned them, in the water or in soil water. Okay, first of all, you have this wonderful thing called the water molecule. It's beautifully put together, beautifully designed, I like to say, in that it has this oxygen, which is fairly large compared to the 2 hydrogen molecules. But there is a delta negative and a delta positive side. The hydrogens hydrogen ions are positively charged. Oxygen oxygen molecules have a slight negative charge. And so when they bond together, it's obviously the overall charge is neutral, but you have a slight negative charge on the one side and a slight positive charge on the other side. So, and you have this angle of the oxygen ions, so they're not symmetrical. It's on one side. So that oxygen molecule then, because of its slightly positive and slightly negative side, it has some very, very unique capabilities. Let's have a look at them. First of all, water molecules, let's have a look at the cohesion first. Water molecules attract one another, and that's because if you have a look here, you could, when water molecules are, when you look at a liquid, the actual negative or delta negative side of that water, often water molecules will somewhat align themselves where the delta negative is aligned to the delta positive. So you kind of have a look at this. Let's have a look here. Now, you know, don't go out and think that water looks exactly like this, but they do adhere to one another because there's this delta minus, delta plus. So the delta pluses are attracted to the delta minuses. So you have a little bit of that attraction between one another. Okay, so let's go the other way. So that's the adhesion or the cohesion between the molecules. Water also attracts, is attracted, adheres to things. So it'll, if you look at a capillary tube, you'll see that the water actually is attracted to that capillary tube. When you wash your dishes, you'll see those little blobs of water that hold on to the dish itself. So it means that these properties make it possible for soil to hold water or retain water, and then for those unique properties that soil has in the holding of water. We also have this phenomenon called surface tension that's associated with the attraction of water particles for one another. So they cohere. And this is a great example. You see this little mosquito over here that's actually sitting on the water, and that is surface tension. It's going to occur at that liquid air interface, and you've basically got a net effect. It's an inward force of the water, and it almost makes that water look like it's behaving as if it were covered by a thin membrane. And so this is really, really important for capillarity, which we'll see in a minute, or in fact in this slide. So there are two forces at work in capillarity. The first force that is at work is this force here, adhesion. And you can see in adhesion, let's try and exaggerate that a little bit. So here's your vessel. Here's a vessel. And you will always see you have a meniscus. And what's happening here is that adhesion, the water molecules are adhering to the side of that vessel. And usually, and you'll see now, the smaller the vessel or the narrower the vessel, the more that force dominates. So that's adhesion. And then cohesion creates this little blob here, and that's pulling that meniscus down, and you have that basic cohesion force. Well, she's got the arrows going up, and we have gravity pulling that whole lot down. So why is that important? Well, let's go and have a look at that, the whole idea of capillary rise, that the height of the rise of this capillary is going to be inversely proportional, and it's predictable, inversely proportional to the size of the vessel. So what does that mean to us in terms of sands and in terms of soils? Well, the major implication here is that the larger particles, like sand, are going to retain less water. There's less attraction between the sand particles and the water particles, and so those water particles, the cohesion holding those water particles together is going to be pulling it down through gravity. All right. When you get finer and finer sands, there's a lot more opportunity for these water molecules to adhere to the soil particles, and so the soil's going to hold it tighter, and there's going to be a lower amount of gravity that's pulling it down. In terms of the clays, you saw that clays, it really, really holds on tightly to the water particles, not only because of the outside surface area, but also because of internal surface area. So there are certain implications that we're going to look at in this. Well, let's have a look at that capillary fringe. It's the zone above the free water table. So this is the free water table that is effectively saturated. So you've got this unsaturated zone, or basically, usually it's the place above your water table. When you're talking unsaturated, you can have a look there. There are spaces between, the pore space is occupied by both water and air molecules. And this is ideally what you want for plant growth. There are some plants that can grow in saturated systems And there are some plants that, you know, are highly drought tolerant, and that where they grow where there's very little soil moisture, but no plants can grow where there's no soil moisture. But you get to this capillary fringe where the water is essentially effectively saturated. You've still got unsaturated parts, but it's essentially pulling up. It's a capillary fringe because it's pulling water up from that saturated zone through that capillarity effect. So there's adhesion going on in these soil particles, and it's pulling it up. In the saturated zone, this is the groundwater, you're not going to find any air in those pore spaces. And of course, the groundwater is the place that needs to feed the rivers. So this is what a natural system should be looking like. All right. What are examples of the capillary fringe? Well, you can see out in the west they irrigate, they use furrow irrigation, and you can see that little layer, over here is where water is effectively pulled up into the soil through that capillarity. Here again you can see an eroded bank in a river, but very clearly this part over here is, if you like, effectively saturated. So those are, Pam's got some great examples over there. Now let's talk about soil water energy, and I must warn you that I'm not an expert on this, and soil water energy is a very, very difficult physical concept, and I think Pam basically taught me about soil water energy, so I'm going to use her explanations and of course her slides. So, but let's think about soil water energy and kind of go back to sort of high school physics and have a look. We've got two kinds of energy. First of all, the first one is the kinetic energy, energy of motion, but because water movement in soils is too slow, we can say that kinetic energy doesn't really play much of a part in soil water energy calculations. We do have the notion of potential energy, and potential energy is the ability to do work. It's stored energy, and this is the most important concept in the movement of water in soils. Okay, so we've got rid of the potential energy, the kinetic energy. So let's have a look at what a little bit about soil water energy. Okay. First of all, just in physics, I think it's the second law of thermodynamics, is all substances, we have a tendency to move from a higher state of energy to a lower one. So you never see, except with capillarity, but typically water is always going to find the path of least resistance, and it goes downhill. Speak to a plumber, speak to a builder, and they will tell you. Soil water is going to move from an area of higher energy or higher potential to an energy of lower potential. So if you wet a patch of soil in, say, the garden or in your yard, and you wet one patch, if that soil around that patch is dry, that water is going to move out, and it's moving from a higher potential to a lower potential there. So it moves from wet soils to dry soils, and we'll see in that case sometimes soil or water can move up. The difference in energy levels of soil water from one condition to another is called soil water potential. All right, so we're looking at soil water potential and soil water energy. Let's have a look at the three things that we've got. The first energy that we have is something called gravitational energy. This is kind of a no-brainer because gravitational energy is the potential for the soil to move, the water to move from a higher elevation to a lower elevation. So in a river or in a stream, or even runoff down the street, you're never going to see the water run up the hill, and it's running purely under gravitational potential. And let's have a look. Okay, so this standard reference state is 0. this standard reference state is higher than 0. So water is, in a sense, higher actually in elevation, and so gravity is pulling it down. Our second water energy that we have is something called osmotic potential. This potential is energy that is exerted by salts in the water. And so, for instance, I think you've probably seen it or heard about it, is if you have a semi-permeable membrane and you separate two bodies of water, and the one body of water you will add salt to, you will find that water will tend to migrate across that semi-permeable membrane to where the salt is, because through Le Chatelier's principle, it's trying to seek an equilibrium. So the height of the water in the salty chamber will rise to the point where the gravitational energy equals the potential energy of the water trying to get across. So you can measure that in terms of water pressures. The final energy is this matrix potential, and this is the potential energy of or the potential energy exerted by water when it's attracted by soil solids. So soil solids is going to be mineral and clay particles as well in that soil matrix. So this is going to be a positive pressure, and this is going to be a negative pressure. So for instance, let's go back to that capillary fringe that we had. So you had the river, okay, and then you had that little fringe going across. You had the top of your soil, and then you had that fringe there. Basically, we've got two forces. The capillarity force pulling that water upwards through adhesion, and then the gravitational force pulling it down. At this point where that fringe stops, in other words, where you get unsaturated soil over here and then your capillary fringe, that point over there is then where the gravitational force is equal to your matrix potential. We're not talking here about osmotic potential, although the amount of salts in the water would probably influence that. But your gravitational potential is going to be equal to your matrix potential in this case. So let's have a look at gravitational potential. This is really a function. That energy function is a function of the gravitational constant and the height above your reference point. And your reference elevation is going to be where your soil is saturated. So gravity is going to be most important in removing excess water from the rooting systems. In nature, your rooting systems do not want to be saturated all the time. Your roots need to breathe, and the critters inside also need a little bit of air in that space. So gravitational force is what pulls that excess water out. Okay, the osmotic potential. Again, while we see this, I've actually explained this, so I won't explain it again. But it's important with plants, and especially, for instance, if you're adding a lot of fertilizer but are not watering, a commercial fertilizer but are not watering, you could find that your plants, because you've got a lot of commercial fertilizer in the soil, they might be exerting a force that draws water out of your plants rather than allowing the plants to pull it in. And so your plants might suffer quite a bit of stress in that. Your matrix potential, again, is that attraction of the water for these soil particles. Real important. Well, they're all important, but your matrix potential is pretty important. Remember, your gravitational force potential is always positive. Your matrix potential is always going to be negative. And so we've got psi G and psi M, okay? Psi M is essentially going to pull that water up. Psi G is going to pull that water down. Okay, so let's have a look at some substances or matrices. you've got very, very high potential substances where water, gravel, and sand, the gravitational potential is the thing that dominates in this case. Clays, good soil structure, and salts are going to exert a more negative pressure or more negative potential energy in a soil. So let's have a look at energy in water potential and texture. So we've got a heavy clay, a silty clay, and a sand. We've got percentage water content on this from dry to wet, and then we've got less negative and more negative. So what you're seeing over here is the potential over here. This is potential is, and this probably should be inverted, this particular slide, but you don't have that much matrix potential, that's negative potential energy being exerted in your sands. You've got a little bit more in your silty clays. It's very, very heavy in those clays. And again, remember when we had that clay in class, that clay blob that we had, you know, try and wet it. It would be very difficult to wet it and then to extract water out of it. Now you could stir it up so that it became a liquid slurry, but you know, in that blob, it was holding very, very tightly to that to the particle. So you see two effects here. Number one, soil water potential is more negative as your texture becomes finer, and number two, it becomes more negative as that matrix becomes more drier. So let's have a look at a couple of other things. Remember that water is always going to move from an area of higher potential to lower potential. So when you have rainfall and it hits the ground, you're going to have downward water flow, either through infiltration into the soil itself, or if there's no place for it to go, it's going to run down, and it's going to run downhill. When you have evaporation from the sun, or evapotranspiration from the sun, or let's talk about evaporation first, is water is going to be heated up, and well, not only heated up, but as water is evaporated from the surface of the soil, you will have that matrix potential pulling up more water from the lower surfaces. It's going to go up from the groundwater, and it's going to evaporate. The big one is this plant water uptake, or evapotranspiration, is that the roots go down, and it's going to pick up water from down here. But if this area over here, for instance, you've got a lot of plant water uptake, this is drier than, say, the bare ground, water will actually start moving laterally. Again, that's from your capillarity forces, or your matrix potential, moving from a higher potential. Remember, you've got the positive being more. Let's go back to that slide. It's going to be less negative. Oops. And it's going to flow to the more negative, from a higher potential energy to a lower potential energy. I hope that makes sense. Water always flows downhill from higher to lower ground, but it also flows from wetter to drier areas, and so in this case, your gravitational force is lower than, it's not pulling the water down, than your matrix potential force. So if now it kind of begins to make sense that saturated flow then is flow that in soils that is under gravitational effect. You've got these, you've got water that's, it's saturated, there's no air particles, and then these are some of the properties of your saturated flow. Unsaturated flow, most of the water movement in soils that top sort of, you know, whatever 2 meters, is through unsaturated flow. Matrix potential rather than gravitational potential is the driving force. So typically it's going to move up, okay? At lower matrix potentials, drier soils, Clay soils will actually, oh, I didn't even know that. Clay soils will transmit water faster than less clay soils. Well, they've got that very high matrix potential, so they'll pull those through quickly. I actually never considered that. Thank you, Pam, for that. So under saturated conditions, water moves in response to gravity. We've talked about that. It's going to mainly move downward through those larger pores, and that's why we want lots of soil structure, those macro pores. Water's going to move downward through that. Under unsaturated conditions, water's going to move pretty much any direction in response to the moisture tension gradient. In other words, again, the matrix potential will, soil matrix potential will dominate. And then you have textural layers that are going to impede soil movement. And we're going to talk about this a little bit later, but you might be surprised by some of the things that we come up with. So, but when soil texture changes, or even soil structure, you will see a change in soil water movement. Okay, let's look at preferential flow, because soils, again, are not these wonderfully uniform things. They're if any, they're very, very diverse and layered and things like that, and you have these inclusions and breaks in them at the macro and the micro level. So you'll often find preferential flow in saturated soils. So for instance, over here you've got a preferential flow above ground, and you've got this furrow, and the water's moving under gravity. You'll find preferential flow underground when you have things like wormholes. So that's why farmers and agriculturalists love these worms, because the worms get down and they become the biological plows, if you will, and they help to move that water down through that soil matrix into the soil, where it can be used later on by the plant. Really important function by these critters, not only earthworms, but other critters in the soil that make those holes. And then, of course, preferential flow can be a problem. For instance, if you have a landfill and you have a break in that membrane, that water is going to move out in that, and around that leak it's going to be, of course, saturated. So water movement, here's some really interesting stuff over here. The water movement, if you have a waterfront in a loam and it comes to a sand, it will wait until that whole loamy layer is saturated. So here we have a loamy layer, and then you've got sand and loam. And that's kind of surprising, because you would expect that through gravity, the water would immediately go down into the sand. So what's happening? Basically, the matrix potential in this loam is going to hold that water up until it's all saturated. At that stage, psi G is going to be greater than psi M, and that's when you're going to have flow down through into the next layer. And there's an application in golf courses, for instance, that will show you. When you have a loam, a finer loam material, and this is a clay over here, then what you're going to have is, as soon as that front hits over here, you'll have preferential, shall we say, potential preferential flow. As soon as it has contact with that clay, it's going to move into that clay. This time, this water is not moving necessarily so much under gravity, but again, psi M, your matrix potential, or the potential energy because of the matrix potential, is pulling that soil down into the clay. All right, so the practical applications. The big one is the golf greens. They will actually put a loamy soil on top, put a little bit of a sand rooting zone over here, and they will perch that whole thing on a gravel layer. And what happens then is the soil would prefer, through the matrix potential, generally to stay in the sand, and that allows them to keep that water in there rather than drain out. I think that's pretty cool, and you can see a similar concept that they use for nuclear waste. Okay, so we've talked about soil matrix potential. There's a related to soil matrix potential in soils, and in how plants deal with this is the whole notion of soil water capacity. All pores, when soil is saturated, all the pore spaces in the soil are filled up. So you have these soil particles, and then all the pore spaces are completely filled up with water. That's what we call saturation. The second state that we want to talk about, and remember, this is in a sense a little bit artificial, but we can simulate it to some extent, is field capacity. In field capacity, basically what you find is that gravity has pulled out all that water through cohesion, but a lot of the water now remains here, adhered to the soil particles. So you have both air and water mixed, and at this point water hasn't been taken up by the plant. Okay, and so that's the second stage. This is, if you like, field capacity is, if you like, the ideal stage. The next stage is wilting point, where the water that you have, there's a lot less of it, but it's still there, but it's at the point where the plants can't access it anymore. They cannot exert enough energy to pull that water into their systems, and that's where the plants, the soil may not be bone dry, but that's where the plants begin to wilt. And then you have something called a hygroscopic state, where you can heat the soils up at 105 degrees for 24 hours, and yet there's still a teeny tiny layer of soil, of water in that soil. For all practical purposes, that soil is going to be dry. Let's have a look at some pictures over here. You've got your saturated soil here, much better picture than mine. You've got your field capacity over here, and then wilting point. So saturated soil, solid and water, sort of these are, they're mixing their units, 100 grams and 40 milliliters. Field capacity, you've got about 20 milliliters of water, and field capacity is going to change for soil texture. Again, we'll come up to that. You're going to get to the wilting point, where you've got a lot less soil, a lot more air, and then finally your hygroscopic point is where you've got water, but it's not really sensible. You'd really have to work hard to burn that off. So an increasing amount of pore space, obviously the drier that soil becomes. So what's this got to do with soil water pressures? Well, the matrix potential that is exerted now, we can actually begin to measure in terms of pressure. And at saturation, your soil water matrix potential, or your pressure, is at zero, because gravity is the dominant force at work. If you had a head of water, of open water above the soil, that pressure would be a positive. At field capacity, so this is superfluous water, and it will flow under gravity. At field capacity, your soil water pressure is minus 10 kPa. So that's 0.1 bar, or 0.01, no, it's 0.1 bar, okay? Minus 10, 0.1 bars. Sorry, minus 1 bar, excuse me. I need to check those units. Let's just work in kPa. And you can see this basically means that the plant has to exert very little energy to pull that water into its root system. Now, as available water begins to reduce, you get to the wilting coefficient of minus 1500 kPa. That's minus 15 atmospheres. So that plant has to exert a force of 15 atmospheres. Think of your car tires. You pump them up to about 2 atmospheres, 200 kPa. So think of a negative 200 kPa plants are still able to exert that force to pull that water up. But this is negative because the plants have to pull it. Now that force is exerted by those water molecules holding very, very tightly onto those particles. Now the water is still available here, but it gets to the point where it becomes unavailable to plants. And just some plants are better than others at doing this. That's why, you have drought-tolerant plants that will do a better job of pulling that water up. But at some point, this water becomes unavailable to the plant. Your matrix potential then begins to increase to minus 3100 bars, kPa, and even higher. So there's a negative force, and it takes a lot of force to try and pull that water out of the soil. Let's have a look at it in terms of available water capacity and texture. Okay, your very, very fine texture. Well, let's have a look at your field capacity first of all. Your field capacity is this. Okay, and let's go back and let's make sure we understand. Field capacity is where you have roughly equal amounts of water and air in your pore space. Okay, and this is where you've got very, very little energy required to pull that water into the plant, or it doesn't have to exert that. So field capacity in terms of volumetric soil water content increases as your texture increases. Now you get to a certain point where that begins to level out there. Essentially the fineness of that soil particle no longer really plays a role in your field capacity. The wilting coefficient more or less increases in a somewhat linear fashion. Okay, now the available water capacity, listen to this. Let's go back here. Available water capacity is equal to field capacity minus wilting point. Now this usually we would say in percentage moisture. So we would measure it in percentage moisture. We often measure it as inches of water per inch of soil. Okay, or inches water per inch soil, or sometimes you measure it as, grams water per gram soil. So there are different ways, but it's essentially a measure of the amount of water in the soil. Watch what happens to your available water capacity as your texture gets finer and finer. Can you see that at some point around the silt loam, it's about the maximum. At some point, because your field capacity is increasing at a rate that is higher than your wilting point is increasing, according to your, as a function of the fineness of your soil texture. But at some point, this field capacity begins to top out. And then what happens is your available water capacity, even though your field capacity might be higher, your available water capacity becomes lower as your wilting capacity continues to increase linearly, if you like, and not quite linearly, but at a higher rate than your available water capacity increases as a function of the fineness of your soils. So when we talk about the ideal soil to hold moisture, that soil texture, it's going to be that loam, that silty clay loam, something like that, that holds onto the moisture, or that's the best for soil moisture in plants. That's because it's got the most available water capacity. When your soils get too fine, it might have a lot of water in it, but it's not going to let it go, because those clay particles are going to hold onto it finely, again because of internal as well as external water pressure. This is the similar, I'm not going to explain this, but this is a similar slide to the other. So available water capacity is going to be influenced by a number of things. It's going to be influenced by texture, by structure. Obviously, structure is going to increase it because macropores will determine a lot of what happens inside that soil as well. The depth to a restrictive layer, because that restrictive layer then is going to place another constraint. Compaction, we've seen that. Why compaction? Because there's less pore space in that soil. Less pore space means less available water capacity. Now this thing, organic matter over here, is really, really important, and we see that for an increase in organic matter, say from 1 to 2% in many agricultural soils, we actually find a doubling of the available water capacity. What organic matter does is it behaves as a sponge, and it just absorbs that water into its own pore spaces, and it vastly enhances the soil function, especially its ability to supply water back, because it doesn't hold onto that water too tightly for the soil roots to get at, but it holds on tight enough that the water doesn't flow down under gravitational force. So that's kind of cool. So looking at soil structure, this is soil structure really influencing not only available water capacity but soil water movement, is that in those granular soils, you've seen some of the granular soils, that fine cottage cheese-like structure or BBs that you see on the surfaces of soils. The granular soils are made because you've got these soil particles held together by those soil glues. You have very good flow that goes down through this particular horizon, and it flows nicely under gravity. If you have blocky structure like this, or prismatic structure where the height of your soil bed or your soil aggregate is higher than the width, you'll also have reasonable flow through this. Okay, water is always going to flow around a soil bed rather than through it. You'll find preferential flow. When you have this subangular block here, which we find mostly in the southeastern subsoils, you'll also find very good flow through it. When you get to platy soils, again, we've seen this, and this is perhaps being kind, because sometimes that water has to go a long way to laterally before it finds a little space that it can work down. So soil flow really is going to be dependent by your soil structure. Platy soils, again, are going to really inhibit water flow down below. All right, let's have a look at soil depth. It doesn't matter if you have a great available water capacity, but it's only going to be for the top 4 inches of your soil. You want available water capacity down through as much as you can of your soil profile. So some of the restrictive layers that you'll find in your soils, and you'll see this in Web Soil Survey, they have a restrictive layer function, and one of them is your depth to the bedrock. Of course, once you hit bedrock, that R horizon, water flow doesn't happen below that. The water will then have to flow through the fissures of the bedrock. Wetness is an issue where you have a high water table. You will find that in many of the coastal plains, where, for instance, your water table may be as high as 20 centimeters below the surface in some of those soils in the cool season. And in hydric soils, then your water table is in fact going to be, that soil is actually going to be covered by it. Restrictive layers, your fragipan, where you've got cemented soils over here, they're not going to let the water flow anywhere. You've got a petrocalcic layer, so it's kind of calcified to the point that it's become like a rock. And then you've got this basal till, which is so dense that it's not going to allow water to go through. When you've got a good soil that's deep with no restrictions, your water is able to flow down into these layers, but conversely, it's also going to be able to flow back up again when those soil roots need it. So if you've got roots that can grow down into this profile, they can access that soil moisture. We've seen evidence of soil compaction in the class, but these are beautiful pictures of what compaction happens. The biggest influence on compaction is if you have heavy equipment or lots and lots of animals walking over or going over a field when the soil is wet. When the soil is wet, it's malleable and it kind of gets squished and squeezed down. There are a lot of hardcore no-till farmers in some areas like the Piedmont that refuse, even if it's going to be at economic loss, they will refuse to put equipment onto soils that are wet because they do not want to encourage compaction. We've talked about organic matter. It's clear from these two samples, and we've done that in the field as well. This sample here has higher organic matter. It's going to influence the amount of porosity and the available water capacity, as I said to you before. The notion of infiltration is how fast water moves into the surface of the soil. So it's from above ground to below ground, and that's going to be much under the, it's going to be under the influence of gravity. Same thing with percolation, is once the water is in the soil, how fast does that water move through that soil matrix? So percolation might be sideways as well, but it's how fast. And we have instruments. There's something called an amusometer or a musometer that allows you to measure that. I think I've got some videos if any one of you wants to watch that. So texture is going to influence these things. Again, now it becomes fairly logical. Structure, a good structured soil, well-structured, granular, or in the subsoil, subangular blocky, is going to allow the soil to, the water to move quickly through the soil. And obviously, texture and structure are going to affect porosity. The larger amount of pores that you have, the faster that water is going to flow through. More and more small pores, it's going to be slower. Again, think of that soil energy potential. When you've got the smaller pore spaces, adhesion is going to be the dominant force, and therefore your soil matrix energy is going to be more dominant than your soil gravitational energy. Here's some infiltration rates, and keep in mind that there's a huge wide variation in infiltration rates. Okay, but these are functions of not only soil texture but of soil structure as well. Again, those two are highly influential. Organic matter management, the more organic matter you can put in your soils, go to City Roots and see what they do. They have huge amounts of organic matter, up to 24%, somewhere between 8 and 24%. They've got very, very good water holding capacity and infiltration rates. There's a practice called no-till, and we found through research that if farmers stop tilling their soils and leave a residue on the surface of that soil, instead of plowing it in or plowing it down, it's almost counterintuitive, but leaving that residue on the surface of the soil protects the soil surface from the sun and also from the action of rain particles. And when rain particles can't directly hit the soils, you're going to have less cementation on the surface of the soil, and over time that soil then is going to become more and more granular in structure, and you will find better infiltration into the soil. Compaction, again, we talked about reduce the amount of time you're spending on those soils, on those fields with heavy equipment or animals. Obviously, civil engineers want to compact the soil because we want to build. I don't want a house built on uncompacted soils. So it depends what we want to use them for. But in environmental applications, we do not want to see compacted soils, whether it's in farm fields or whether it's in a forested area. Erosion control, again, how do we control erosion? We've got to try and keep the soil covered as many days of the year as possible, either by canopy or residue. and we want to keep a root in the ground. We want to make sure that that soil structure is good and in place. We don't have any compaction. Erosion is very much a function of runoff. In fact, if you increase your runoff by a factor of 2, typically your erosion is going to increase by a factor of 10. We often kind of think in terms of, well, what do we do with the runoff? And I think that is an incorrect way of handling the problem. We should be thinking about how do we increase infiltration. That's where water is naturally supposed to be. Okay, there are many ways of measuring soil water content through the gravimetric method, and you've done that in calculations in class, basically taking a soil sample, putting it in an oven at 105 degrees C for 24 hours, bringing it out, weighing it before and after, and then we know how much water there was. We've got these other things over here, and of course a lot of these electronic measurements are coming out and very handy to farmers and vegetable growers and things like that to say, well, do I need to put more water in the ground or shall I stop irrigating now? So these are lab methods over here. Those are field methods over here. So soil water retention curves, and we've kind of talked about it earlier on in terms of the functions of sand, silts, and clays or soil texture, but your soil matrix potential is not going to be the same for all textured soils. So sand, your soil matrix potential tends to drop as your soil moisture. Okay, wait a minute, hang on. As your soil, your soil matrix potential, as your soil, let me start again. As your soil moisture drops, your soil matrix potential gets to a certain point, and there, by that stage gravity has taken over. So there's a precipitous drop. As soil moisture drops, you have an increase, a small increase in soil matrix potential, but because that soil, there's not that much cohesion going on with those big grains, you don't have that. Whereas your matrix potential, as your clay, soil moisture in your clay decreases, you have this massive increase. You know, you're getting to millions of kilopascals over here. That shouldn't be H, that should be kPa over here. So you can see that's just, these are what we call soil water retention curves. Okay, soil water management, nutrient availability. Obviously, when we're using commercial fertilizers, we've got to be careful not to put too much down. Too much down is going to influence that osmotic pressure. All right, and we'll talk about. So these are the 4 things, and there's a separate slide for each one of them. So nutrient availability. If you have a water deficiency, number one, you've got reduced microbial activity. A lot of the microbes in that soil matrix are aquatic creatures, so they need water to function. When you have less water, of course, you can't deliver your nutrients to the plant, and of course then you're going to reduce the plant's metabolism. For instance, corn, one of the symptoms is that their leaves begin to curl. When you've got excess water, you have reduced aeration, and you know, when your plants get their feet wet, often they will die if kept in that saturated place for a long time. And then with an excess of water, you have something called the process of denitrification, where you've got microbes in the water profile, in the soil profile, that act on a nitrate ion, convert it to nitrous oxide, and then to nitrogen gas, and it goes back up into the atmosphere. We'll look at that a little bit more when we look at the nitrogen cycle. So those are some of the effects of water on nutrient availability. You're not going to be able to grow much in terms of cash crops in a soil like this. Okay, you can see, you know, these tracks over there, not really good. Denitrification has happened over here. Nitrogen usually makes those plants nice and green, and so when you've had denitrification in very, very wet soils, there's a lack of it, and you're going to find that kind of thing happening. This might also be the effect of nitrogen leaching out down under gravity into the soil or into the aquifer. So they have something. I'm not going to talk about this too much because I think the first thing we have to do is not use engineering practices. Engineering practices are the last resort. The first thing we need to do is how can we increase infiltration. But we have structures that people have used in the past. In the Midwest and in the low country, often they've drained the swamplands, especially in Carolina Bays, and then you have ditches around those fields, and then underlying those fields are things called tile drains. And these are basically pipe channels with holes drilled in them where the water then moves to, and then that water then drains under gravity to these ditches, and it's either pumped away or it's led away by gravity. Obviously, people wanted to grow crops in areas where the water table was high, the soils were very fertile, and they did that. But tile drains, a lot of us are trying to get rid of those artificial things again, because when you have nitrates thrown on a field and you've got water moving under gravity, or when you've got nitrogen thrown on the field in form of ammonia, it oxidizes to nitrates, it moves under gravity to these tile drains and ends up in our river systems and our aquifers. So we're trying not to do that anymore, and that's why we're trying to protect our wetlands and help the wetlands get back to their natural functions. Here are some of the examples of diversions and drainage ditches. Nitrogen and phosphorus, we won't talk about that too much right now, but nitrogen and phosphorus in agricultural systems can be a big problem. You see this big red blob over here. It's a huge issue. Nitrogen tends to leach out into the aquifer and ends up in either surface waters or the aquifer, and you'll find concentrations of nitrogen above 10 parts per million in the Midwest, where pregnant women have to actually drink bottled water so that their babies don't get something called blue baby syndrome. So that's pretty bad. Phosphorus doesn't leach out, but it's attached to soil particles, and when soils are eroded because they're tilled and uncovered, those end up in the riverways, and they eventually end up, look at that, they end up in the Mississippi and end up down here. Sediments, again, are an issue, and wherever you have intense agricultural practices and indiscriminate use of things like pesticides, you're going to find that those end up in the system. Pathogens are another story entirely. They're often very short-lived, but will be associated with land-applied manures. Okay, so how do we protect our water quality? Well, apart from this, again, increase infiltration. Cover the soil, keep a live root in the soil as many days of the year as possible, and a lot of your water quality problems will start decreasing. Nutrients, if you have to put nutrients on the ground, and these are for farmers, they have to be very careful about the rate, timing, the source of those nutrients, and the placement. How do they put them on the ground? So we're not going to worry too much about the manure incorporation. Crop residue management means when they're managing that residue, instead of tilling it in, they leave the residue on the soil surface, and they will then, that residue becomes an armor. When we talk about conservation practices, perhaps the most important practice is this idea of cover crops. And when you keep a soil covered, then your soil, you've got a live root in the soil, and you've got this canopy above maybe that residue layer, and when you've got raindrops coming down, the raindrops then don't hit the soil and run off, they get infiltrated into the water. Pesticide management, well, that's another story, but there's a notion or a practice called integrated pest management, where you don't spray just because you need to spray, but you will only add, manage for pests if you actually see them on the ground. And then there are a whole lot of other natural ways to deal with pests and not just spraying. Okay, Water is also a very good filter, and when rainwater lands on certain soils, the clays, for instance, are negatively charged and will actually attract many of the many contaminant particles. But it's not only an inorganic filter. There are many microbes in soils that will act on many of these really, really nasty substances. That over time, those substances will actually get broken down, not through not through inorganic methods, but through these soil microbes, and often with the help of the sun. Okay, so to summarize, we've spent about the last hour and a bit. We've looked at the water cycle, the water molecule, adhesion, cohesion, surface tension, energy that is related to soil water capacity, how we measure the soil water content, and finally what the implications of those things are for soil water management. I trust that you have learned something from these, and please bring questions to the class. I think in class we will be doing some calculations on how to calculate soil, the amount of water in soil in those various ways. Please enjoy your week, and I will see you next time.